Hello and welcome to the Craig M. Burge 2020 Virtual Design Day. We are Project 1950 with the Medical Device Fluid Management Connecting System, sponsored by Ziridium Medical Devices. Here's our team. We're going to introduce ourselves from left to right.
My name is Kate Mizell, studying engineering management.
My name is Misome Anami. I'm a mechanical engineer.
My name is Cassie Kimball. I'm studying biomedical engineering and I'm the team lead.
My name is Stratton Yatrin. I'm studying mechanical engineering.
My name is Mihir Patel and I'm studying biomedical engineering.
My name is Cullen Walsh and I'm studying mechanical engineering.
So here's a quick look at the overview of our project with the poster. If you want to take a moment to pause, this has a summary of all the information that's going to be covered later in the video, but let's just jump right in. So let's take a quick look at the design from the top level. Ziridium wanted us to design the next generation of their feeding tube connection system. The purpose of the system is to help insert nutrients and medicine directly into the stomach for people who are unable to eat or ingest food through normal means. You can see the system here. The important things to point out are that the low-profile gastrostomy tube is the silicone medical device that is inserted in a surgically created stoma, kept in the stomach by an inflated silicone balloon, and then you have a detachable extension set consisting of, most importantly, a valve connector and a feeding tube, and with our design, the locking piece. And so we'll go into a little bit more detail about the old design and then further into our solution.
So here is the old system design of the low-profile gastrostomy tube that was designed by the Ziridium Medical. The current design has the valve connector, which is inserted into the top housing, and it is locked at a 90 degree. On the right GIF, we can see how the old system design works. On the left-hand side, we have a continuous assembly, which uses a slow feeder, and it has a narrow feeding tube, while on the right, we have a bolus assembly, which uses a syringe for the faster feeding, and it has a wider feeding tube. One of the major issues with this old design was that once it's locked, it is not able to rotate freely, and the tab on the valve connector was breaking off. So the scope of our design was to design a new locking mechanism which will prevent inadvertent disconnection while it is able to rotate 360 degrees for the feeding tube, hence it doesn't get tangled up. It also has to maintain a low profile design, and anyone with no prior training should be able to use that. Hence it has to be an intuitive design, and it will be used in a at-home care setting. So now Mas will explain in further detail about the design concept and the final design.
We developed many different designs in order to meet our design goal and conduct two case studies to find the most reliable manufacturable design. Now we're going to look at the phase one design concept. There's three designs. Left, you can see the two quad design. In the middle, you can see the closing keyway design. In the right, you can see the external locking sleeve design. And we discussed with experiment to choose the least amount of part required will be strong, simple, and reliable. We ultimately choose the external locking sleeve because it was the simpler design and the least part required. For phase two design concept, there's three designs. The first one is external screw design. The second one is external quarter turn design. And the third one is an internal quarter turn design. We select the external quarter turn design because when we tinkering with the prototype, it was the most reliable from all the design. And we eventually evolved to the multi-thread hybrid design. For the early prototype design, we had a multiple design iteration 3D printer on a personal 3D printer with a PLA and polycarbonate filament, and we incrementally changed by rapidly prototype generation to produce the best result. The next is a result of rapid prototyping. We prototype it out with a PLA and polycarbonate. We also produce a SCL prototype with 1:1 scale. Next, we will discuss about final prototypes.
Here are a few images of our final prototypes. Let me walk you through all of the components and features. First, we have the locking piece, which is the only piece that we've added to the previous assembly. It comes in two identical halves, each with a threading track cut into it. The locking pieces assemble around the stem of the valve connector. You can see on the valve connector in the middle that there is a circular shelf that keeps the locking piece in place. So it can't be removed axially, but it can still spin. We've also maintained a significant amount of the geometry of the actual valve connector, as the previous tip worked very well with Ziridium silicon valve. You can see here how the multi-start thread connects to the top housing. The top housing has two tabs which meet into the two threads in the locking piece. This multi-start design allows for intuitive screw-on use, but also makes alignment easier and reduces the risk of cross-threading. We're also, with the two halves of the locking piece, able to create thread stops, which prevent over-tightening and also give a good tactile sensation once the system is fully locked. Here's a video of our final prototype in action. You can see it screws on, and then any manipulation of the valve connector will not undo that lock. So you have no chance of it tangling or coming undone when you don't expect it.
The intended material for our system is polycarbonate. Ziridium has experience with the specific kind of polycarbonate and has found it to be durable, biocompatible, and it meets their shelf life requirements. Finite element analysis suggests the design and material will be more than adequate to pass strength requirements. SOLIDWORKS has tools for performing structural analysis, which were used to ensure structural integrity when the assembly is pulled on axially. This case was chosen as it is expected to be the system's weakest direction. This analysis showed us how much stronger our new valve connector is predicted to be than the old tap design. The maximum stress in the new valve connector is 16 times less than in the old connector. The new design's ring spreads force over a much greater area. We were also able to run a worst-case flow test with the final design diameter. The minimum required flow rate for our system is 240 cc's per minute. Simple hand calculations suggest to us that water has to flow through our system at 0.8 meters per second to meet this requirement. This speed depends on the smallest choke point in our system, which here is the tip of the valve connector. Our design easily exceeds the flow rate requirement by 65%.
In addition to meeting our flow rate requirement, all geometry requirements for the design have been met through simple inspections, as demonstrated in one of the videos previously shown. We were unfortunately unable to verify all the system requirements due to the effects of COVID-19, but we are confident in our design's ability to pass when they become possible again. One of the major surprises for the team is finding out how much it costs for high-resolution plastic manufacturing, which is over $3,000. With that discovery, we learned how important it is to perform budget analysis early on. Another lesson we learned was to double, triple, and quadruple check with manufacturers as requirements and capabilities change over time. We were able to overcome our problems by doing the analysis to see if we can adjust the dimensions for production and meet our requirements, and also remembering to stay calm, do the math, and have a backup plan. Here are the deliverables to our sponsors. We will have the last 3 items delivered by May 5th. In conclusion, we have met our project goals of designing a new locking mechanism that prevents inadvertent disconnection with the ability to rotate 360 degrees and also maintaining low profile of the system. Moving forward, we have a provisional patent application drafted and the production on the horizon. At this time, we would like to thank our sponsors and our mentor for providing us assistance in dedicating their time and effort for our team to be successful.